In this video, I'd like to talk about the math question of the day for March 17th, 2023. And with this problem, we need to state the domain of this function y is equal to the square root of 3x minus 4. And to answer a question like this, you do need to have an understanding of algebra and maybe even pre-calculus, depending on when you learn about domain and range. So at this point, go ahead and pause the video, see if you can work through this on your own, and when you're ready, unpause the video and we can go through this together. Now, assuming that you have at least attempted the problem, let's start working through it. And if you do have suggestions for future questions of the day, feel free to leave those as comments. Now, domain, we need to ask ourselves what this actually is. And when graphing things on the coordinate plane, the xy axes, the domain concerns the independent variable, which usually we just call x. And essentially, the domain is just asking which x values can be graphed. Or in other words, we can ask which values of the independent variable can we plug into this function and actually evaluate it and get some type of real number. So with square root functions, they have issues with the domain. In fact, there are two main cases where functions run into issues with the domain. One, like I mentioned, is the square root. And actually, let me use the function notation. When we have a square root function, the x value needs to be bigger than or equal to 0 to plot this on the xy axis here. Since if x is a negative number, let's say f of -1, then we get the square root of a negative number, and this is the imaginary unit. And it is possible to graph a function like this, but not using the standard xy plane. We would need to use more advanced techniques to deal with that. So for high school math, the domain is typically restricted to positive x values, but 0 works as well. If we put in 0 here, we get the square root of 0, and we know that 0 multiplied by 0 is equal to 0. So that would just be 0. So if we plug in 0 here, the square root of 0, like I said, is just equal to 0. So that's okay as well. It's just when x is negative that we have issues. And the other function that we would need to concern ourselves with when looking for issues with the domain would be some type of rational function. And the simplest one is just 1 over x. And x cannot be 0. We cannot divide by 0. And this is a value that there is no possible way to graph. This is impossible because there's no way to define what division by 0 actually means. So even when including complex numbers, this is not possible to ever graph. Whereas in this scenario, if we extend the numbers that we're using to complex numbers, there are ways to plot these imaginary numbers. So when dealing with domain, we just need to look for square roots or division by the variable x. And we know in this case, we're dealing with the square root function. And we know the parent function for the square root function is going to look something like this. If you plot points, if you plug in 1, you get back 1. If you plug in 4, you get back 2. It's not drawn perfectly, but you can get a general idea of how this works. And of course, 0 will evaluate to 0. So the origin is involved in this graph as well. And when we multiply our independent variable on the inside by 3 and we subtract 4, these essentially will transform this function. The adding or subtracting will shift it left or right, and the multiplication will scale it horizontally. So essentially, we are just shifting this graph around. So we essentially need to figure out where this new boundary point is. And to do that, we want to know effectively when the square root starts to become negative, or when the values under the square root start to become negative. And we should look at when this is 0. since anything less than those x values will produce the square root of negative numbers, and anything greater than those x values will produce the square root of positive numbers, which we can actually plot. So we need to figure out when this expression under the square root is equal to 0, and from there we can figure out that boundary point. So we want to set 3x minus 4 equal to 0, or we could write it in a different way. We could say that this expression needs to be a positive number. It can be 0 as well. And the way to express that is with an inequality. We can say that this expression has to be bigger than or equal to 0 if we want to actually plot it on this coordinate axis. And from here, we can just solve for x. We can add 4 to the other side, so that 3x is bigger than or equal to 4. And lastly, dividing everything by 3, we find that x is bigger than or equal to 4/3. And once we think we have an answer here, we think this will be our domain, the x values, which we can actually graph, we can test this out. We can look at x values that are less than this, and we can look at x values that are greater than this and see if we can actually plot those points. So let's make a little bit of room, and I'll just rewrite our equation here. Y is the square root of 3x minus 4. And if we set, let's say, x equal to 1, when we plug this in, we get y is the square root of 3 times by 1 minus 4, which is the square root of minus 1, which we know is the imaginary unit. And this can't be plotted, which makes sense. We expected this value of 1 to not be in our domain since it's less than 4/3. And for it to be plottable, for the coordinate point to actually exist on the xy axis, the x value needs to be at least 4/3 or more. And we can look at the other side of this as well. We can plot the point, let's say x is 2 or 5/3 or something slightly bigger than this, or we can even plug in this point. But if you plug in 4/3, you'll just get 0. And if we plug in 2, we get y is equal to the square root of 3 times by 2, which is 6. Subtract 4 from that, and we get the square root of 2. And this is a real number. It's an irrational number, but it is a real number. And we can plot that coordinate point at 2, comma, the square root of 2. So we tested values on both sides of this inequality, and we got back values that actually made sense. So we can feel confident that this is the domain of the function. These are the x values that can actually be graphed on the coordinate plane.